Hello, everybody, and welcome to today's webinar. On behalf of Infineon Technologies, Vector, and Tasking, we are excited to present the AURIX Drive Core AUTOSAR bundle today, an innovative collaboration that seamlessly combines hardware, software, and toolchain expertise to simplify your automotive software development workflow. My name is Florian Süßmer. I'm from Tasking, and I will be the moderator of today's webinar. Before we start, I would like to share a few quick housekeeping notes. So here on the next slide, you can see that today's session is being recorded and will be made available later on demand. So if you would like to revisit any part of the presentation, you'll be able to do so at your convenience. Just visit tasking.com and you can see the webinar later on demand. Throughout the webinar, please feel free to submit your questions. We have a special Q&A function here in Zoom. We will collect them and address as many as possible during the dedicated Q&A session at the end. Now let's meet our speakers. I'm pleased to introduce 6 experts from Infineon Technologies, Vector, and Tasking, who will guide you through today's topic. So we have on the left top side Frank Kremer. He's from Tasking, Director Customer Success. Hello, Frank. Then we have Matthias Scheidt, also from Tasking, a Senior Application Engineer. We have Alexander Igelhaut from Vector, a Program Manager, and on the right side, his colleague Florian Wandling, also from Vector, Principal Partner Manager. And following Florian, we have Lisa Kamp from Infineon, Senior Manager, Product Marketing, and Eamon Marev from Infineon, Staff Field Application Engineer. So our focus today is clear. We will highlight why the AURIX Drive Core AUTOSAR bundle is exactly the solution you need to tackle common challenges in automotive development, such as licensing management, compatibility, and choosing the right partners for scalable and safe system development. By the end of the session, you will walk away understanding how the Drive Core bundle tackles key challenges like licensing and compatibility, what each partner contributes to the bundle and how their expertise builds a strong ecosystem, and finally, how you can easily download, deploy, and start benefiting from the solution today. Before we dive deeper into these topics, let me take a moment to introduce the 3 partners behind the Drive Core and the unique strength in this collaboration. So first we have Lisa Kamp from Infineon. Over to you, Lisa.
Thank you very much, and also hello from my side. I'm Lisa, and I'm proud to represent Infineon Technologies today, together with my colleague Eamon, and he will walk you through more details later on. At Infineon, we are also proud to play a leading role in this Drive Core collaboration with our trusted partners, Vector and Tasking. Why Infineon? Infineon is a global leader in automotive microcontrollers, so it provides the right foundation for the Drive Core bundle. With our market-leading AURIX microcontroller, also known as the Drive Core, and the Infineon software, the MCALs, we provide a seamless integrated solution with Vector's AUTOSAR stack and Tasking's toolchain. AURIX has been designed to meet the needs of the modern applications, automotive applications like ADAS, xEVs, and also next-generation EE architectures. It's also compliant to the highest automotive standards, such as ISO 262 and ISO 21434 for security, which ensures robust performance. The Drive Core bundles offer seamless integration with pre-tested hardware and software, so it takes much of the complexity, which means you can get your innovation faster to market.
Thank you, Lisa. Next, representing Vector, we have Florian Wandling, Principal Partner Manager. Florian, tell us more about Vector and its role in this collaboration.
Thank you. My name is Florian, and I have the honor to represent Vector today, together with my colleague Alex, who is doing the tool presentation later on. So I really have to say that we as Vector are very proud to be part of that collaboration. We have a very long relationship with both partners, Infineon as well as with Tasking, and it has been a success story over decades. If I would need to summarize what Vector actually stands for, I would say we simplify the development of embedded systems. So that is our North Star, and everything what we do is actually heading into that direction. So what does this mean? So we provide our customers with a software ecosystem to create software-defined systems that can consist of embedded software building blocks, but also as well of tools. In the embedded domain in the past, we have been mainly offering software building blocks. Our customers then created a software platform out of it. As a good example, I would mention AUTOSAR as one product. We call it MICROSAR Classic. We have listened to our customers, and what we strive to do next is actually to provide a software factory approach to do the next step. A completely integrated but open ecosystem of tools and services to continuously develop, test, and deploy software. With that initiative, we will take more responsibility bringing software to the road. You can visit our website, our events to learn more. In this particular drive core bundle, we have integrated our safety certified AUTOSAR software, and we have ensured that it is pre-tested, robust, and completely interoperable with the Infineon AURIX hardware and tasking tools. We know that efficiency and time to market is a key requirement, especially in these days, but also compliance with strict safety standards like ISO 26262 is important. Simply put, using Vector's products integrated in the drive core bundle means streamlined system integrations with fewer roadblocks, letting you focus on creating and deploying your products earlier and faster.
Thank you, Florian. Now, last but not least, representing Tasking, we have Frank Kremer, Director Customer Success. Frank, tell us about Tasking and its unique contributions.
Thanks, and good day, everyone. Tasking is proud to support this collaboration with our market-leading technology and complete development ecosystem, purpose-built for the AURIX microcontroller platform. It comes with dedicated PPU libraries and an integrated runtime environment that simplifies multi-core programming and communication across the drive core cores and the PPU in the TC4 devices. Combined with high-performance code generation, this lets you create optimized hardware-specific code. And last but not least, our Blue Box offers comprehensive debugging and tracing features for efficient troubleshooting. To let you start exploring these capabilities, our application engineering team, and I want to specifically mention Matthias, who is with us here today, developed a demo and integrated it into the Drive Core AUTOSAR bundle, so you can focus on using the bundle and not setting up the environment.
Perfect. Thank you to all of our speakers for those insightful introductions. And now it's clear how each partner's unique expertise has come together to create an innovative, integrated solution. Now, let's dive into the details and explore how the AURIX Drive Core AUTOSAR bundle tackles key challenges in automotive development.
Yes, thank you very much. Today's automotive development comes with many challenges, but also to keep things simple, let's focus on two of the most frequent barriers we consistently hear also from the industry. First, managing complex licensing, and second, achieving seamless compatibility. To the licensing aspect, we understood how challenging it can be to manage multiple licenses across different hardwares, software, and tools. And then also managing multiple suppliers and providers can be difficult, and it also slows things down. With the AURIX Drive Core AUTOSAR bundle, it makes it easier because we combine all three licenses in one software bundle, which saves time and also reduces complexity. To the compatibility, this is a big challenge today, but also in the shift to software-defined vehicles. By combining the right hardware, software, and tools, it's important. This is important, but also seamless integration is often the hardest part. So with this Drive Core software bundle, we solve this with pre-tested and pre-configured components. And with Infineon hardware and software, Vector's AUTOSAR, BSW, and tasking tools, we ensure everything works together smoothly from the start. All right, then let's go to the benefits of Drive Core Bundle. Thank you very much. Let's take also a closer look about the benefits and the bundle content. So first, the Drive Core Bundle represents the combined expertise of 3 industry leaders, Infineon, Vector, and Tasking. The software package includes Infineon software, which is the MCAL, stands for Microcontroller Abstraction Layer, Vector's industry standard AUTOSAR, and Tasking tailor-made compilers and debugging tool chains. The benefits for you is a simplified licensing management across all partners because all licenses are included. We guarantee compatibility across the components and everything works together smoothly. And in the end, for you as a customer, this leads to reduced time to market because it enables to speed up your development and you can focus on delivering new features. Along with these components and the Drive Core Bundle, we also have created guides, getting started guides, code examples and demos, and also support resources to ensure that you can get it up running quickly. Then let's take also a closer look to how you can get the Drive Core software bundle. So it's pretty easy. So you only need to Google for it, Infineon Drive Core. Then you click on the first Google search, you scroll down, you click on AURIX Drive Core. And then you will find down below under Explore and Get Started. Yes, there it is. The AURIX Drive Core AUTOSAR bundle. You click on it. And then you get forwarded directly to Infineon Developer Center. First, you must log in first. We will do this quickly. And there you will find the bundle. And then you need to request this. You click request. It's added to the cart. All right, request, click. And then we only need from you some details, your name, your company, your project. We fill this out. This is just for demonstration purposes. And then you also need to say what is your operating system from your laptop. And then for supporting reasons, also accepting the terms and conditions. And then you send a request. That's basically it. We will receive a notification and then we can grant you access to the bundle. All right, then let's also have a closer look to finalize this, how this version of Drive Core comes together. The short video will provide you a clear overview of the features and the benefits of the Drive Core bundle.
So thank you for watching. What you just saw highlights how the Drive Core AUTOSAR bundle simplifies the development of automotive software by reducing your workload on licensing, eliminating compatibility concerns, and aligning 3 trusted partners into one seamless solution. You can focus on building the next generation of vehicles confidently. So with this, let's move to the highlight of today's webinar. Next, we will hear directly from the experts who developed the Drive Core bundle. Our first speaker is Ayman from Infineon, who will walk us through how the AURIX microcontroller is the foundation for this solution. And I will have to stop here and then let me share. Just a second. Ayman, over to you.
Thanks, Frank. So let me start by introducing myself. My name is Ayman Maref. I'm a field application engineer working at Infineon, situated in Hanover, focusing mainly on AUTOSAR software offering for our AURIX MCU family. So now let's have a look on what you will get from the Drive Core AUTOSAR. Let's briefly walk through today's agenda. We will begin with a short demo overview, then examine the functional block diagram to understand the end-to-end flow. After that, we will review the hardware setup required to run the demo, and we will conclude with the tools and workflow that takes us from configuration to a running binary on the board. With the agenda set, let's begin with a demo overview to anchor the scope and objectives. This demo emulates an adaptive cruise control system, so-called ACC. It continuously monitors the distance to the vehicle ahead and adjusts the ego vehicle speed to maintain a selected, safe following distance. In our setup, sensor-like inputs are currently emulated to create repeatable scenarios. These inputs are filtered and processed to derive control-relevant measures from which the system decides whether to accelerate, maintain speed, or decelerate. The decisions are visualized on hardware using LEDs today, with a clear path to transmitting decisions over Canon future phases. With the overview in place, let's look at the functional block diagram to see how data flows end to end. So this slide summarizes the end-to-end functional pipeline. As we see, we are in a multi-core system. So our complete application or our complete demo is running on 3 different cores. In this case, it is core 0, core 1, and core 2. Core 0 consists out of 2 software components, the standalone mode software component, the data acquisition software component. Core 1 is consisting of data filtering software component and data processing software component. And last but not least, core 2 with decision-making software component and vehicle control software component, which is then acts on the I/O directly. Let's go a little bit deeper on what these software components are meant to do. So on core 0, the standalone mode software component synthesizes sensor-like frames, such as the distance to the lead vehicle and the relative speed, and hands them to the data acquisition component. Data acquisition normalizes and timestamps the input, perform basic range and unit checks, and publish them via typed AUTOSAR RTE sender receiver ports for a downstream consumption. This interface-driven approach keeps data exchange explicit and reduces coupling between components. On core 1, 2 components deliver the mid-pipeline computation. So the data filtering component applies plausibility checks and smoothing to remove noise and transient spikes, ensuring that signals are robust. The data processing component derives control-relevant quantities, most notably the headway gap, the gap error relative to a chosen target, and the closing rate. These derived signals are produced consistently and exposed through well-defined interfaces, so the next stage can make decision based on fresh validated data. And on core 2, the decision-making component evaluates the filtered and derived data against simple control policies to select one of the 3 discrete actions: accelerate, maintain speed, or decelerate. The resulting decision is forwarded to the vehicle control component, which handles actuation on the hardware. For this demo, we map decisions to dedicated LEDs via the DIO module. Accelerate is mapped to LED 1, which is located on port 33.0. Decelerate mapped to LED 2, which is located on port 33.1, and maintain speed is mapped to LED 3, which is located on port 33.4. This makes the system's behavior immediately visible for the user, and in the next phase, the same decisions will also be packaged as CAN PDUs using the AUTOSAR COM stack, allowing observation on the path in addition to the onboard LEDs. With the data flow clear, let's turn to the hardware setup required to run the demo on the target. To run this demo, you need an Infineon triboard with a TC4D9 COM package and a TC4X compatible hardware debugger, such as MiniWiggler or Tasking Bluebox IC7. Provide a stable power supply and connect the debugger via the standard DAP interface as shown here in the picture. This is all that's required to flash the image, run the application on target, and observe the behavior via the onboard LEDs. So no additional peripherals are needed for today's demonstration. If you plan to explore the CAN roadmap later, have appropriate CAN cabling and a compatible transceiver ready, but these are not required for the current demo as mentioned. With the hardware ready, let's walk through the tools and workflow that takes this demo from configuration to a running binary. We start in DaVinci Configurator. We ingest the ECU configuration provided as AUTOSAR RxML files. Alongside that, we include the static deliverables from our partner Vector and also from Infineon. So Infineon delivers the MCAL static files, and Vector delivers the MICROSAR basic software, including the MICROSAR OS static files. And in parallel to that, DaVinci Developer defines the software components, their ports and runnables, and generates the RTE, which binds our application interface to the basic software. DaVinci Configuration then produces the project artifacts, which are the generated files, that together with the static files and our demo application source code forms the complete build input. Next step, the Tasking SmartCode toolchain will compile and link everything into an executable ELF image. Using a TC4X compatible debugger, for example WinIDEA, will help you flash the software into the hardware and let you observe the system behavior. For today's demo, you can verify outcomes directly on the hardware via the LEDs, and you can also monitor live variables in the debugger environment to confirm the end-to-end data flow and decision logic. When changes are made, such as adjusting an interface or adding a signal, the cycle is simple. You have to reconfigure, regenerate, rebuild, and reflash, and then re-verify the behavior, keeping the configuration and generated artifacts under a simple flow to be reproduced. In the next segment, our partner Vector will provide a concise walkthrough of Drive Core and its main components. Alex, stage is yours.
Thanks a lot, Ayman. Let me show you in more detail what you can find inside the Drive Core bundle for the AURIX TC4x. I downloaded the bundle already to my PC and unzipped it into this folder. Let's step into it. On top level, you find a detailed documentation containing all the pictures and diagrams you have seen from the presentations before, including some additional steps how to run and execute the bundle later on your side. Next to the document, there's the actual bundle called Drive Core AUTOSAR. Here you find all the different modules which were already described by Ayman before, starting from the components from the Vector MICROSAR Classic. So you get the whole list of all the different components here which you can use to build up your project. In addition, we also added our DaVinci configurator, which you can use to configure the basic software for your specific project needs. In the demo folder, you find the actual demo applications for the ACC and also the configuration for the respective system. We also provide with the bundle more detailed documentation for all the vector toolings like the DaVinci configurator and also the MICROSAR Classic stack. The make support here in the next folder helps you in generating and building your project and also using it then later in your on your PC, on your device. From our partners, on the one hand side Tasking, we have also included the SmartCode compiler for compiling your project at the end, and also the MCALs from Infineon, which comes with the bundle for the TC4x contained in the third-party folder here. Let's have a closer look at the demo folder here. I opened the project already in the Visual Studio and jump here into the demo folder. The actual demo is part of the folder which is called Start Application, and in here you find the folder Apple, where you will actually find the source code and the configuration for the specific project. More details how to execute and build this will come later on from Matthias. From my side, just one more important point here to add is that you can see here the central make file, which gives you the possibility to configure the high-level project path. For example, here you see the path for the compiler, which you can change if you want to use a different version or your own compiler. In this case, it points to the compiler which is part of the bundle. As a next step, I want to show you our DaVinci developer and how you can configure and create the respective applications. So let me start the DaVinci developer first. By opening the respective project, which is under the demo start application, and the file is called start application DPA, which contains the project specific configuration for the DaVinci developer. The same file will be later on used for the DaVinci configurator, so it contains the whole configuration of this specific project. Let me open that one here. Now you see already on the left-hand side the topics which you can configure in respect to the application. Here on the top left you see the component types which reflect the same structure as you have seen in the diagrams before. Starting from the ACC data acquisition to the data filtering, data processing, and so on. By referring to the documentation and scrolling down to the actual place where we see the connection between all the modules. So here on slide 9, you see that the data acquisition component, software component, has a connection to the data filtering component. And that's what we see in the DaVinci developer as well. So the data acquisition component here on the top has a port which provides the distance measurement from the actual vehicle in front, here seen as a provide port prototype. On the other hand side, the data filtering component uses this data, so the measured distance raw data, as a receive port prototype here, and can then do the actual filtering of the data. That's basically how you can build up all the connections between your software components and also define the behavior of the actual components inside. Once you're done with configuring all your components here, you can then go to the next phase and generate the actual templates. As part of the bundle, this implementation already happened before, and you can find it under the actual application code here in the demo, start application, Apple, and then sources. So let me open one of the files here. For example, that's the software component for the data acquisition. And in here you find the same structure as you defined in the DaVinci developer. For example, the distance measurement, which we just discussed, with the raw value, which is written to the RTE. After configuring the application code, the next step is to configure the respective basic software. This reflects or is presented in the document here. So the workflow for configuring the actual basic software. On the right hand side, there's the static code from us, Vector, the MICROSAR basic software, and the Infineon MCAL. And on the left hand side, there's the actual configuration and generation step. To do that, we use our DaVinci Configurator 5. Let me open that one as well. I have opened already the start application DPA file. As I mentioned before, it's the same as for the developer. Now in the configurator, you have a different view on the project. So here you have the configuration for the basic software and the operating system. And that's also what I would like to show you now, what you have already pre-configured in your project. Let's open the runtime system here on the left side and go to the place where the OS configuration is available. So first of all, you see here, you have 6 different cores for the specific microcontroller. For the demo, we don't use all of them, but you can use them to extend it later on. In the tasks, you will then see the actual task to call the applications later on. Here we have 3 ACC tasks, one on core 0, one on core 1, and one on core 2, which is then mapped to the respective application software components, which are distributed between these 3 cores. Afterwards, you can also have a closer look how the actual tasks are mapped into the system by clicking on the task mapping here on the left side and having a closer look in the application components here. For example, let's have a look at the data acquisition. By clicking on it, it directly jumps to it, and you see in which priority and which core this specific runnable is executed. In this case, it is under the task on the core 0. Finally, you can validate your project here on the top left, following by generating the actual configuration for the respective basic software modules. This will then be the base for building your binary, which you can flash on your TC4x device later on. So saying that, let me quickly summarize what you will get as part of the bundle. So first of all, you get a very detailed documentation, how to run and build the project. You have the entire folder structure here already available with all the pre-configured files. And then you also get the tools around that to generate and build the project till the end. And saying that, I would hand over to Matthias to show you in more detail how to build the demo application and how to run it on your respective device.
Thank you, Alexander, for handing over to me. In the next round about 10 minutes, I will provide an overview of how to get the AURIX Drive Core AUTOSAR bundle running on the hardware. To give you a better orientation, I'll start with a short overview. Let's jump to the File Explorer and navigate to some relevant folders. Those folders that contain essential files to get the application running on the target. I start in the root folder of the bundle. Here we find SmartCode, which contains the compiler. The demo folder that contains the start application. And herein, the relevant directory is this Apple subdirectory. It contains application-specific files. Source includes application source files in case you want to make some adaptations to the application. And here are also some files belonging to the build environment, such as make files and batch files like this m.bat that is used to compile the application. Back in the demo folder, we also find a WinIDEA folder, and this one carries a pre-configured WinIDEA workspace that can be used to flash, run, and debug the application. The AURIX Drive Core AUTOSAR bundle already comes with a pre-compiled binary. Here we can see the ELF file. That means you can flash and run the application on the target without compiling it yourself. However, if you want to make any changes to the application, for example, if you change the configuration of MICROSAR Classic components in Vector DaVinci Configurator 5 and regenerate the dynamic configuration files, or if you modified some application logic, or if you extend the project by adding your own source files to the build environment, you need to recompile. So let's have a look at the compile step. To speed things a bit up for this webinar, I've already pre-compiled the application. I just delete the existing binary here. Now to compile the application, I open a terminal in the demo folder. And I run the batch file m.bat to invoke the compilation via make support. And please note, when you compile on your machine for the first time, it can take several minutes. Now it compiles the source code. And after the linking process has finished successfully, we have again our binary, the ELF file here. As the binary is available, we can run it on the target now. A quick overview of the hardware setup. We have a host PC where we have downloaded and extracted the AURIX Drive Core AUTOSAR bundle, connected to the target hardware via debugger. We recommend to use our debug solution, Tasking WinIDEA and the Bluebox IC7 platform with an Infineon triboard TC4x9. To get WinIDEA, download the latest version from the Tasking homepage. Depending on whether you choose the installer or the portable version, install or extract WinIDEA. And double-click the icon to start it. The Drive Core AUTOSAR bundle comes with a pre-configured WinIDEA workspace. Navigate to the workspace folder at Demo WinIDEA and open the workspace from there. To ensure that the setup works properly, let's check a few parameters and conditions. Go to Hardware, Debugger Hardware. Here we can confirm that the correct debug platform is selected. In this case, we're using an IC7 Max. Under communication, we verify that WinIDEA can access the hardware. The green indication bar confirms that WinIDEA is communicating correctly with the blue box. It's also recommended to perform a quick license check under Tools, License. And in the configuration dialog, we run the test. And it should indicate that the license was acquired successfully. In order to check some application-specific settings, we go to Debug, Configure Session. In Applications, we see our app. The operating system is configured to AUTOSAR. With this OS awareness, WinIDEA is capable to provide some additional OS-specific information, for example, the current state of a task or information regarding priorities. In simplifies, the compiled ELF file is referenced. This is where WinIDEA retrieves the debug information from. In the SoC configuration dialog, we see the target device, a TC4D9XE. The workspace is configured as an SMP, a symmetric multiprocessing setup, utilizing all TC cores. In memory spaces, we can see that the application is assigned to the SMP core cluster. And in program files, the binary is listed again. These are the files that will be programmed into the flash. Now we can download the application to the target by pressing the download button. WinIDEA initializes the hardware and programs the binary to the target. The download process succeeded. The program counter is set to the application entry point. CPU 0, our startup core, is kept in stop state, and by pressing the run button, the execution of the application starts. On the triboard, it can be observed that the LEDs start to blink now. These LEDs are indicating activity of the executed application. With WinIDEA, we now can control, observe, and debug the system. In the watch window, we can see several global variables. The relevant values are ACC underscore decision making underscore decision, measured distance, and safe distance. The application included with the Drive Core AUTOSAR bundle mimics an adaptive cruise control system. A standalone mode component injects simulated sensor data. This sensor data is a measurement of the distance to a preceding vehicle. The simulated sensor data is passed through and processed by several software components distributed across the cores. The data acquisition component acquires this sensor data on core 0. On core 1, there is data filtering and data processing, and decision making and vehicle control on core 2. The application continuously tries to keep the measured distance as close as possible to the safe distance value, making decisions such as accelerate, decelerate, or maintain the current speed. Let's adjust the safe distance, the value the system aims to maintain. If we increase it, the vehicle needs to slow down to enlarge the distance. We can see that the decision stays at decelerate for a moment, and the measured distance adapts to the new safe distance value. Let's change the safe distance from 3K to 8K. We can observe how the system reacts as expected. It now maintains the measured distance around the value 8000. Now we can explore the full debug feature set. We already modified some variables. We can set a breakpoint, for example, at ACC decision making get decision. The system halts. Core 2 is stopped because the breakpoint hit a function that was executed on that core. The other cores are suspended due to the core synchronization. You can step through the application on the C source. But also in the disassembly. You can inspect the call stack. And in the AUTOSAR OS plugin, we can see the state of the current task and a lot of additional useful information. The used SoC, the TC4D9XE, provides extensive on-chip trace capabilities. If you're using a Bluebox IC7 Pro, or as in this setup, an IC7 Max, on-chip tracing can be used to gain deep insights into the runtime behavior of the system. WinIDEA includes the analyzer, which can be used for tracing. When clicking the record trace button, tracing is started. Trace data is streamed off the TC4, collected by the Bluebox and transferred to WinIDEA, where the analyzer decodes and processes the data. In the profiler timeline, we can now investigate the runtime behavior of the system in detail. We see a timeline of all OS tasks, the ACC task on core 0, followed by those on core 1 and 2. You can also see the states of the tasks, and the same with runnables. the full chain, data acquisition, filtering, processing, decision-making, and vehicle control. You can also see some statistics like average, minimum, and maximum execution times. Tracing is an incredibly useful tool to observe the system behavior, detect bottlenecks, and optimize performance. If you want to go a step further, you can integrate this in Vector's timing design and verification solution, TA Tool Suite. And that's it with the hands-on tour of the AURIX Drive Core AUTOSAR bundle. If you have any questions, feel free to ask and contact us at any time. Thank you.